Today we're going to revisit some of the OpenCL programming concepts. We're going to talk about two topics, host programming and kernel programming. Let's revisit some of the concepts in OpenCL programming on the host side. Mainly we're going to talk about context, kernels, buffers, and so on. At the very beginning of our classes, we talked about OpenCL platforms, context, devices, and the queues associated with devices. We want to emphasize here that devices from different platforms cannot be placed in the same context. Platforms are provided by the vendors to identify the OpenCL devices and also support the operation of these devices. On a physical platform, we may have different OpenCL platforms provided by different vendors. In principle, these different platforms cannot be placed in the same context because often the time the vendor provided libraries and platforms do not operate with each other nicely. When we build a host-side OpenCL application, we can have multiple contexts, and these contexts can in fact use resources from different platforms that reside on the same physical platform. Now, it might be a little confusing about the platform we're talking about. So we're really referring the differences between the physical platform, which refers to a physical machine and multiple devices that are plugged into this machine. And OpenCL platforms are the kind of the conceptual or software platforms that each vendor provides to support the operation of their OpenCL devices. So in principle, on the one physical machine, you can have multiple OpenCL platforms provided by different vendors. Using the host-side application, you can build a context which will rely on one of the platforms. So you can have a context built on the FPGA OpenCL platform provided by Intel. At the same time, you can build another context built on top of a OpenCL platform provided by NVIDIA. Within one context, you can have multiple command queues. Now, these command queues are the main mechanism that the host-side application communicate with OpenCL devices. And we mentioned earlier that each of the command queue is associated with a device. And on these OpenCL devices, we can use object, and oftentimes memory object, and these objects can be shared by multiple queues. So you can have a memory object in a global memory, and you can have multiple queues that are going to access the memory object through different devices. Devices, we refer to the compute unit and also the processing elements within the compute unit. So it may happen that on one physical platform, for a vendor's OpenCL platform, you may have a global memory that is shared by multiple compute units. As a result, it's possible to share these memory objects by these different OpenCL compute units through different queues. To share an object across multiple command queues will require the application on the host side to perform appropriate synchronization. Because the OpenCL specification does not have a requirement on the synchronization point across different platforms and different devices. Now we want to use this diagram as an example to illustrate some of the concept. So what we're showing here is one physical platform. You can think about one big server. And you may have platform A and platform B, these two OpenCL platforms. You can think about this is a FPGA device that supports OpenCL, and this could be a GPU device that supports OpenCL. So on this machine, you can run a host-side application. In this application, you can in theory, instantiate three contexts: context 1, context 2, context 3. and each of the contexts will use some resources on this OpenCL platform. You can use one or two devices from this platform A to build context 1. You can also use another part of the resource from platform A to build context 2. And these arrows pointing from the device to these contexts can be viewed as the queues that we were talking about. You may notice that for this particular device on this platform A, it supports 2 queues, which are instantiated into 2 contexts. Well, this is possible, but we do have a requirement on this device. It has to provide proper synchronization to these commands coming from different queues. Now, we want to talk about another interesting API that we were probably going to use. In the past, we create kernels in programs where each OpenCL program, we mostly have one kernel function with a certain kernel function name. There are cases that you can have multiple kernel functions in the same OpenCL program. That is to say, you have mykernel.cl, and in this kernel program, you may have multiple functions, function A, function B, with different names. So this particular API, CL create kernels in program, will create kernel for every function in the program. So instead of creating kernel one by one, you can use this API to create kernels for all the kernel functions that we put into the same OpenCL program. So the API takes one argument. The first one is the program object. Then we can specify the number of kernels and the kernel objects we want to instantiate, and also the number of kernel functions created by this API. And then we can use getKernelInfo to go through these kernel objects to verify these kernel function name, the number of arguments, and other information related to a kernel object. Here's an example. We declare a list of kernel objects and a kernel object called found kernel. And then we have a character array that holds the kernel name. And we have an integer that specifies the number of kernels. So what we're going to do here is we're going to first call create kernels in program. We take the program object as the first argument, and then we only supply the number of kernels, the last parameter, to this API. After this API is completed, the variable number kernels will return with the number of kernels that the OpenCL finds in this kernel program. And based on that, we will create an array of kernel objects. And again, we make the call second time. So we create kernels in program, supplying the number of kernels, which we found out from the first call, and then with the list of kernel objects. If this second call is successful, then we will have the list of kernel objects instantiated in this kernels array. Next few lines within this for loop, we're going through the kernels objects and look into the kernel function names of these objects. We can then find out the kernel name. Then, based on your need, you can say, I want to compare the kernel name with this multiplication. If you have a kernel that is named mult, and then you will be able to use this if statement to see if indeed this particular kernel function is successfully instantiated. And at the end, after everything's done, we'll release all the kernel objects. In reality, you may not need to release kernel objects this early. Chances are you have a lot of statements. Well, before this releasing the kernels, you'll be using the kernels to execute kernel functions. We have used CL set kernel argument. This is a very important API that is used to instantiate the kernel arguments. This particular API takes a few arguments. First is the kernel object, then the index of this kernel argument, and then the size of this kernel argument, and then finally the value of this argument. Now, in terms of the value, this last argument points to the data that will be transferred to the kernel function. We can give this API several different ways to pass the argument values to the kernel functions. We can simply pass a pointer to a primitive data. Let's say we want to pass an integer, and we can put this integer in a integer variable, then use the pointer to this variable as the last argument. In this case, we're simply transferring the simple primitives to the device for the kernel function execution. In a different case, we may pass in a pointer to a memory object. This will transfer significant or complex data, which we store typically in a memory object. The other case is similar. We can use the pointer to a sampler object, and this sampler object is closely related to image objects. In this example, we define an object that will in turn defines how the images are going to be read. In some cases, we do not have to pass in any particular value to the kernel function. Instead, we'll just put null pointer as the last argument. In this case, we're transferring no data from the host, and the device will just use this null pointer as indication. It will reserve memory in its local address space for the kernel argument. And that's how typically we reserve local memory space within the kernel functions. In the next few slides, we're going to be talking about the image object. Image processing is a major priority in high-performance computing and also in embedded systems in dealing with image operations. OpenCL provides a very special type of memory object, which is specifically for holding pixel data. That is the image object. We use image object, but they are still a memory object, so we can declare using CLMem structure. Image objects are created with the same configuration flags as for the buffer objects. For example, we can choose to allocate space on host, or we can use pointer host copy to make copies of the initial data, or we can use read and write, or both read and write to specify the access types to these image objects. For images, we are talking about 1D, 2D, 3D textures, frame buffer, or just a simple picture. So there could be different specific format for these images for different image operations. And the elements of image objects are defined from a list of image formats that we will look at shortly. First, let's look at this API that creates the image object. It's similar to create buffer. We have a CL create image, which takes context as the first argument, the memory flags, and then we're going to be using the image format. This is a predefined data structure to describe the format of the image. Then we have this image description, which is also a predefined data structure. And then we have the actual data that we could be using to initialize the image object. And then we have a return value for error indication. The first two arguments are in fact very similar to those used to create buffer objects. If the flags is 0, the default is CLMem read and write. The third and the fourth arguments are so much related to the image object that we'll spend a few more slides to talk about them. But essentially, the third argument identifies the format properties of the image data to be allocated, and the fourth argument is a pointer to the structure that describes the type and dimensions of the image. Don't worry about these arguments for now. We're going to be looking at some details in the next few slides. The next few arguments, for example, the data and the error, are basic for the transferring or initializing the pixels, and also for checking about errors. In the previous offerings of this course, we talked about CL create image 2D and CL create image 3D. Those two APIs are now obsolete since OpenCL 1.2. But if you still have these APIs in your original programs, chances are they will still work. But in the future, you may want to change those APIs to use this new one, CL create image. So let's look at this image object format. It is a structure defined within OpenCL specification. Essentially, this image format consists of information about the order of channels and also the channel types. Let's look at these two individually. Overall, this image object format is to identify how image pixels are stored in memory. There are two things we need to consider when we store an image in memory. First, channel order. We look at these images in terms of channels because each pixel potentially have their colors encoded. If it's black and white picture, you only have the grayscale. But if it's a color picture, you will have essentially red, green, blue, and other information regarding their color and also opacity. So this channel order basically defines how we're going to store these channel information for each pixel. This is an enumerated type, and most of its values involve these basic colors and also the alpha information, which is the opacity information. So you may have CL RGB. So from the name, you can refer that this is where we want to store these color information in the order of red, green, and blue. And this one, CL RGBA, is to store the color information red, green, blue, and also followed by the alpha. So as you can see that we have different ways to store these information in different sequence, and we use these predefined values to indicate that. Others added bit padding represented by this number X. So you may have RGX, RX, etc. The intensity measure is to specify the metrics on the alpha, the opacity, the transparency of these colors, and they are independent to these colors. And this CL luminance is used for grayscale images. The other piece of information is to specify, for these color channels, how many bits we want to represent the value in this channel. So this is to specify the channels and in terms of bit levels. For example, we can use simply unsigned integers to represent the values in this color channel. This image channel type specifies how an image channel is encoded in binary. And we're gonna be using these different values to say how we want to encode the color information. For example, here, CL unsigned integer 8. This is to say that we're going to use an unsigned integer, that is 8-bit, to represent the color information in a particular channel. Here in this slide, we want to show you an example to specify a normalized unsigned 8-bit channel RGBA image. And because we want to store these color information in a sequence of red, green, blue, and alpha, and we're going to be using CL RGBA as the channel order. For the channel data type, we're going to be using CL unnorm int 8. If we go back, we can look at the table to see unorm int 8 is to use the component as a normalized unsigned integer. The memory layout of this image format will be as follows. It will be for each pixel you have this RGBA in this sequence, and each color channel we just use 1 byte to encode that color information. Similarly, if we use the same order for the channels, but we change the image data type to CL signed integer 16, then the memory layout is a little bit different. we still have this red, green, blue, alpha in the sequence for describing each pixel. But now each channel here takes 2 bytes because we're using now signed integer 16-bit. So this will be 2 bytes, and the next color channel will be starting at offset 2, then 4 and 6, and so on. When we look at images, we typically know we have 2D images because when you're talking about image, it's 2D. But in fact, interestingly, in OpenCL and in many other many other image processing applications, oftentimes people are thinking of 3D pictures. When we talk about 3D pictures, we're not talking about really the ones you view using 3D glasses in the movie theaters. Instead, we're talking about different layers of 2D images. For example, here we have a 2D image of height y and width x, and you can essentially have multiple of these images, and they are called sometimes slices, and each slice will be identical in terms of height and weight, but when you have more of those, we now have a third dimension, that's the depth dimension z. So when we operate on image objects, we sometimes refer to 2D images, and sometimes we refer to 3D images, and in that case we have essentially multiple of these slices stacked together in another dimension. So we use this CL image descriptor to describe how these image objects are going to be laid out. For example, how the image, are they 1D images or 2D images or 3D images, or simply an image array that refers to a collection of image objects. Also, for each of the images, we can specify the image width, height, and depth in units of pixels. And also for the array size, we can specify how many images in this array, and these images could be 1D or 2D. And then we have another parameter called row pitch. This is the scan line pitch in bytes. So that is to say that for each row in this picture, for each row in the image, how many bytes we're talking about. And we have image slice pitch. It is to refer to the size in bytes of each 2D slice in the 3D, or the size of images in 1D or 2D array. So this essentially is the number of bytes you need to describe the images in this 2D slice, or the size of each image in a 1D or 2D array. For the levels and for the samples, these are right now reserved to be 0. And finally, this memory object is the valid buffer or image object that you can put here as a pointer that you can refer to. In most images, you can use simple formulas to determine how many bytes are in a row by multiplying the bytes per pixel and by the pixel per row. But sometimes this does not work well to provide you the precise number of bytes to describe this image, because the rows may contain trailing bits, so you may have some paddings to fill out some of the pixels that's not well defined, and also you may have rows that need to be aligned on memory boundaries. So that's why in this create image API, we use row pitch argument that will identify how many bytes are in each row. Slice pitch identifies the number of bytes in each two-dimensional image or slice. If row pitch is set to 0, OpenCL will assume the value equals width times the number of pixels in bytes. If slice pitch is set to 0, its value will be set to the row pitch times height. So in those two cases, when you have row pitch and slice pitch, if they're set to 0, basically there's no padding, no alignment, You can use the simple formula to calculate the number of bytes using the dimensions of this image and their pixel sizes. Once you have an image object, you can use getImageInfo to further check the information about this image object. You can find out the bit size of the pixels. You can find out the pixel width, pixel height, and depth, and also row pitch, size pitch, and also you can find out the image format and some other information as well. In general, you can get information about a memory object using getMemoryObjectInfo, similar to the image objects, but this is more generic because you may not use this memory object for images. You may have this memory object for other data structures, but still you can use this getMemoryObjectInfo to query the properties of this memory object. For example, you can look at the memory flags to find out how this memory object was allocated. Also, you can use this host pointer to find out the host pointer that refers to the memory object's data. You can get the size of it, you can get memory offset and reference count and all other information. When you have a buffer object, as one kind of memory object, you can use read buffer and write buffer to pass data around between the host memory and also the device memory. When we have been using these before, just to recap that we use CL enqueue read buffer to read data from the buffer object to some region in the host memory, and CL enqueue write buffer is doing the opposite, which is to copy the data from the host memory to some part in the buffer object. We can use this offset to indicate which exact location in the buffer object we want to perform this copy. So if you have a case that you only want to override a certain region within the buffer object, you can then use this offset to indicate that. Just a quick review: if you use these enqueue commands before, you notice that many of them have this number events, wait list, and event. As we talked about these earlier, these are the parameters, the arguments for these APIs to specify what are the events that this API has to wait for. This API will not complete until all the events on the wait list completed. And once this API itself is completed, it will generate an event using this CL event, this last argument. We can do the same thing for image object data. You can see that we just replace this read buffer now with read image, write buffer now with using write buffer. Write buffer is now write image. The first arguments, queue, the memory object, the blocking or non-blocking, these are the same, but we now have a few more arguments, and specifically for the image object, we have now origin, we have region, we have row pitch, slice pitch, etc. These are specific for image objects because, as we mentioned earlier, that now image objects, even though in memory you can view it as a linear array of bytes, but conceptually these image objects are organized in terms of slices and pitches, and each slice we can say we want a small region that part of this image, so we can use this origin to specify the starting point of that smaller region. And also we can specify the region to indicate from that origin and what will be the size for this particular region that we're interested in. Another interesting API is for operating on rectangular regions in memory, we can use read buffer rec and write buffer rec. And in this case, it's similar to the image operations. And now we just use the origin for specifying which particular starting point we would like to retrieve data or write data. And also we use the size information, the region, to specify how big is it. This is not used very often, but just interesting API that you may find it useful in some unique situations. Mapping memory objects. We can recall that in C programming, when the OS supports, we can map files content in process memory and read and modify it. That's the case we use memory mapping. For example, if we want to modify the contents of a file, we can place the file's content in process memory and map a specific memory region to that content, and then use memory operations to read and write to that file through these memory operations. OpenCL provides a very similar mechanism for accessing memory objects. We can map a memory object on a device to memory region on the host. If we do that, then instead of using CL read buffer or write buffer, we can just use this memory pointer on the host to read and modify the memory objects for that particular memory object. Once it is mapped, we can read and modify the memory object on the host side using the pointers we obtained through the memory mapping. And particular APIs we're going to be using are, for example, CL enqueue map buffer. We take the command Q as the first argument, the buffer we want to map the pointer to, and we will supply memory map flags, for example, read and write, supply the size for the buffer to be mapped, and also we can use these map events to indicate what are the events we need to wait or what events to be generated, and finally the error code. This API will return a pointer, and this pointer is a host side pointer, and which will be then used to perform memory operation. You can use this pointer later to do memory copy or assign values, and then these memory pointer will take effect by basically perform operations on the buffer that is mapped. We'll use also this mapping operation to map image objects, and once that's done, we can use the unmapped memory object to kind of revoke the mapping that we have obtained through the earlier APIs. As we mentioned earlier, that the return value from this memory map API identifies the start of the memory on the host, and also for later for the unmap operation to revoke the mapping. To work with memory mapped data, it takes 3 steps. First, we enqueue the memory map operation using either map buffer or map image, and then you can perform data transfer from or to the mapped region using a function like memcopy. Once the memory operation is done, you don't need this memory object anymore. Then you can unmap the region by calling this enqueue unmap memory object. Memory mapping improves the performance over regular read and write operations because you don't explicitly put read and write operations into the command queues anymore, and it's simpler in terms of programming on the host side. Here is a whole list of memory objects operations you can use to copy data between memory objects. You can do enqueue copy buffer from you give the first argument command queue, then source buffer and destination buffer, two memory buffer objects you can use to specify where the data copy is going to be from and where it's going to be copied to. Similarly, we have copy image and copy buffer to image, copy image to buffer, and copy buffer rectangular. This illustrates the copying of buffer objects. So here we have a host and device. On the device side, we have two buffers. These are the buffer objects allocated. And we can use CL enqueue copy buffer to copy the data from one buffer to another buffer. And then we can use CL enqueue map buffer to map this buffer to some part of the memory space on the host side. Then by using this mapped memory pointer, we can then use memory copy to copy this mapped region, which is in fact the buffer to itself. And the mapped data will be copied from this mapped memory region to the final result array.